My name is Dan Meneley. I retired from a 42-year career in nuclear science and engineering in 2001, but still teach occasional engineering courses at UIT. Energy supply, that is an engineer's job to do, is ultimately a societal issue. How much energy? What kind? What collateral damage is acceptable? And so on. Many questions remain. This talk covers only one job done by engineers: turning rocks, that is uranium ore, into gold, that is societal wealth. This miracle of modern alchemy was discovered by scientists about 75 years ago. But Mother Nature did the job first, more than 1 billion years ago. I will speak only the green text in this short presentation. You can read the rest of the words faster than I could possibly speak them. My subject today relates directly to uranium fission as a source of energy for use by people. The red words on these figures show the general areas of technology associated with the information presented on the slide. Science refers to the wording of the 2009 Ontario Grade 9 curriculum. It is known that the uranium on Earth was formed about 6.5 billion years ago. Uranium was produced long before the Earth was formed. It is among the heaviest atoms known today. Uranium occasionally emits an alpha particle, that is a helium nucleus, and thereby changes to thorium-234. More rarely, it breaks into 2 or 3 parts in a process called spontaneous fission. Much of the energy that heats the Earth today comes from this radioactive decay of uranium and thorium that is mixed in the rocks of the Earth. The half-life of uranium-238 is 4.5 billion years. Just over 0.7% of today's natural uranium consists of the isotope uranium-235, with a half-life of 0.7 billion years. Old radioactive atoms, like people, are not the same as when they were young. Over half of the uranium formed in our local part of the universe has now decayed to lead-206, and is no longer radioactive. Energy and mass are the same and can be converted from one form to another. When fission occurs, a large amount of energy is released, mostly in the form of heat. The same happens when gasoline is burned in your car, but in much smaller quantities. Uranium provides heat with which we can make electricity. The only 2 nuclear bombs used in war were dropped by the U.S. in 1945 in Hiroshima and Nagasaki. Both of these cities have recovered and are typical of other large Japanese cities. International agreements have been effective since then in preventing nuclear weapons use, even though more than 30 million people have been killed by so-called ordinary weapons in the many wars since 1945. Steady production of fission energy is produced by setting up a chain reaction. Power is held constant by controlling the number of neutrons in the reactor and therefore the number of fission events per second. The heat released is used to boil water. High-pressure steam is the turbine's working fluid. Atoms are very, very small. It takes more than 6 trillion fissions each second to light one typical light bulb. Here we see the energy flows in a uranium-fueled power plant. Doing this job efficiently and safely is a task for professional engineers. Engineering itself is a statutory profession, the same as law and medicine in Canada. Each engineer is charged with the task of creating products that benefit at least some part of the society. he or she is held responsible professionally for the integrity of these products. One small fuel pellet can toast about 1 million slices of bread in the course of a year. Fuel pellets and fuel bundles are shown in the next three figures. Fuel pellet is where fission happens. When manufactured, the fuel is made of natural uranium dioxide, but when the pellet is removed from the reactor, it contains less uranium-235 and less uranium-238, plus fission products and a significant amount of plutonium. After removal, the fuel pellet decays towards stability. It decays quickly at first, and then more slowly over many, many years. Millions of fuel pellets are contained in each CANDU reactor. Their useful product is heat, which is the result of the continuous chain reaction that takes place in the reactor. Because this fuel bundle has not yet been in an operating reactor, Dr. Garland can carry it safely. But fuel bundles are loaded into and unloaded from each CANDU reactor every day using a computer-controlled fueling machine with the reactor operating at full power. When the bundles are unloaded, nobody comes near them. Automatic fueling machines place them safely into a water-filled storage tank. Here is a picture of Darlington on the shore of Lake Ontario, east of Toronto. These four reactors produce over 3,500 megawatts of electricity, or about 5 million horsepower. After fuel bundles cool off, the simplest thing to do is to put them back where we first found the uranium. We can do this, of course, but there may be wiser ways to manage this material in the long term. Electrical energy is delivered to you, the customer, approximately 20 seconds after a uranium or plutonium fission event occurs. Uranium fuel is inexhaustible. We have enough uranium to supply all of the world's energy needs for at least 600 centuries, and thorium is even more abundant in the Earth's crust. Of course, it's not all sweetness and light. Fission products and the residual heavy elements must be isolated from the environment for a long, long time. But today, technology exists that would allow us to use nearly 100% of the potential energy in uranium and thorium, and therefore make waste disposal much simpler.